So it's my pleasure to welcome Professor Anirban Mukhopadhyay, my colleague from IMSC, and he's going to tell us about beyond uniform distribution.
I'm going to use the word equidistribution as well, so nothing wrong. Yes. So start by thinking about a rectangular billiard table. So this is a picture I could just download, and if you hit a ball, then it just goes to the boundary and reflects with some rule of reflection, and maybe it reflects several times before hitting a ball, or it may not hit another ball and just stops due to friction. Now let's imagine a table where you don't have friction, so it keeps moving if it doesn't hit a ball. So then some question arises that if can it just keep moving, or it should hit another ball after some time. That's the question, and let's try to put it more mathematically. Will the ball come to close to every point on the table? And the answer turns out to be yes, if the starting slope is as in real line, because as of the straight line, the ball is moving in straight line, that's what I'm assuming, if the starting slope is irrational. And this is a consequence of a classical theorem by Kronecker, which is this. So if alpha is a real rational number, then if you look at this multiples of alpha, alpha 2 alpha, 3 alpha, 4 alpha, etc., and look at the fractional parts of that. So those fractional parts lie between 0 and 1, and they form a dense set. So that's the reason this is going to happen if you start with an irrational slope. Now, if now we know that this is a dense set, so we would also like to know that how these points are distributed in 0, 1, whether they are equidistributed. So what's our notion of equidistribution? So our notion is that if we look at a subinterval, it should get the correct proportion of elements. So the proportion of points belonging to a subinterval should depend only on the length of the subinterval. So if you take a bigger interval, it should get more points. If you take a smaller interval, it should get less number of points. So it should only depend on the length of the interval. And that's a definition, so I won't really call it, I'm not going to call it, you can call it equidistribution, I'm going to call it uniform distribution. So a sequence xn lying between 0 and 1 is said to be uniformly distributed if this happens. So what is this? So if you count the first n points and count the points which are in this subinterval AB, and then divide by the number of points, which is n. So that proportion should converge to the length of the subinterval as you consider more and more points. So this is what is uniform distribution. And these are examples of sequences which are uniformly distributed. So the first example is n power into alpha. Is uniformly distributed if alpha is irrational, and n power alpha is also uniformly distributed if alpha is not an integer. So you can think of n, say, square root of 2, or even in square root of n. That's uniformly distributed. In all cases we are looking at only the fractional part, because this might go up beyond 1, so you are going to look at the fractional part. And also another example with log n to the alpha. So there is a classical criteria to check if some given sequence is uniformly distributed, which is known as Weil's criteria. And this calls for an evaluation of an exponential sum of this form, and you need to check that it goes to 0. So I am not going to use much exponential sum in the rest of the talk, so I am not going to talk about this much. Okay. So let's again come back to the billiard and ask a further question. So now we know that if a ball starts from a point with an irrational slope, so after some time it's going to hit a ball wherever it is placed. So it comes close to any point actually on the table. Now the point is how much time it's going to take. Will it come to a particular point very quickly, or is it going to take a lot of time? So that's the question, that how much time it takes to come to a particular point. Let's put it more mathematically. So mathematically speaking, we are looking at the rate of convergence of this counting function. So how fast this converges to the length of the interval, which is the expected value. So this question is of course being asked for sequences which are known to be equidistributed. So that the limit, we know that the limit actually converges to b minus a, the length of the subinterval, and we now want to see how fast it happens. And this is what is called discrepancy. So this definition of discrepancy is just nothing, it's just look at the counting function and subtract the expected value, look at the difference, and then take supremum over all possible subintervals. So looking at discrepancy is an interesting problem. Of course, as I already said, that you are going to look at discrepancy for a sequence if you already know that it's equidistributed. It's a finer question. In fact, if you can prove discrepancy goes to 0, it is equidistributed. But you want to say how fast it goes to 0. So the first example is n alpha. The one in Kronecker's theorem. So that we already know that it's equidistributed and or uniformly distributed, and so we want to calculate the discrepancy of that sequence. So we multiply. So alpha is an irrational number. Suppose it's an irrational number, and you take integral multiples of it and look at the fractional part, and then calculate the discrepancy. This turns out to be n to the minus 1 plus epsilon for any given epsilon with a constant depending on epsilon involved. And this happens for almost all alpha, almost all in the sense of Lebesgue measure. So for the set of alpha for which this does not happen forms a set of Lebesgue measure 0. That's what it means. And let's calculate for n square alpha. For n square alpha, it is n to the minus half. The first one is best possible, that is known to be best possible. N to the minus 1 plus epsilon is the best possible. But in very few situations, we can actually calculate best possible ones. Okay. Now, I'm going to look at some strange objects. Oh, no, how much time I have? I actually didn't check the watch.
You have about 12 minutes.
Oh, okay. I should go slow actually. Yeah. So, so to define what is called generalized polynomial, I need two notations. So this the first notation is given a real number. The square bracket x is the integral part of x. So that is the largest integer smaller than this number. So if you look at x on the number line, look to the left. Yeah, actually this is the left for you. So look to the left and pick the integer you hit first. So that's the integral part, and the fractional part is just the difference of that number and the least integer. So integral part can be negative, but fractional part is always going to be positive. And now we know that polynomials have two operations, addition and multiplication between numbers and the indeterminate. Now we are going to introduce these two operations into polynomials, and that's what is generalized polynomials. They are going to look like this. So these are examples. So there are many variations possible. So I just read out the first one. So first one is just 3x, so that's just a standard monomial as usual monomial. But the second one has this bracket operation. So we are looking at x square, multiplying it by square root of 2, and then look at the integral part, not the entire thing, but the integral part of it, plus a constant. That I am just writing pi to be dramatic, but it just can be any constant. And also the fractional part operation. For example, the third generalized polynomial has a fractional part operation. And also nestings are also possible. The second example has a nesting. So it has a nest of these square brackets. So you are looking at the integral part of 5x, multiplying it by another number, adding something, and then again looking at the integral part, and this kind of nesting is possible. So these very strange objects appear in many places, and many of them are known to be uniformly distributed. They generate uniformly distributed sequences. So there were lots of dynamical study on this. So my point is here is not going to go into those things, but what I work on is to calculate generalize the discrepancy for these generalized polynomials. So I look at very simple generalized polynomials because things are known for that only, and even there it's a bit complicated. So I am going to look at a very simple generalized polynomial, no nesting or just one bracket actually. So Px is a usual polynomial of degree d with rational coefficients, and then we consider this sequence where I take two real numbers alpha and beta. So look at this Pn, where P evaluated at positive integral values multiplied by alpha, then the integral part, and then multiply by beta. So that may be of course bigger than 1. So you would look at the fractional part then. So every time we are looking at the fractional part so that it lies between 0 and 1 whenever we are talking about this uniform distribution. So it's known that this is uniformly distributed if 1 alpha beta, these three real numbers are linearly independent over rationals. So that's known. So that's the situation where it is uniformly distributed. So we can ask what the discrepancy is. And discrepancy, so we are going to, so that's a rate of decay. So we would like to find an upper bound, as I have already shown you examples that we would like to find an upper bound, then we know how fast it decays. It may not be best possible, but we want to find some upper bound which goes to 0 as n goes to infinity. So this is a result with Olivier Ramare and Kashi Vishwanathan some years back, where we could prove that for almost all reals, the discrepancy of this polynomial. So this n has a very strange looking exponent. So I am not going to read it, but better look at an example. So when the degree is 2, this turns out to be n to the minus 1 over 15. So that's a negative exponent. Of course, you would have to get a negative exponent. A positive exponent is meaningless. So that's the kind of thing can be done. This is not a best possible result. So lot of improvement is expected. And this depends on what I am calling irrationality type. I am not explaining. So it depends on how irrational this pair is. So But in the end, for almost all, you can prove this result. It actually depends on the irrationalities. Okay. So we also looked at this same question for primes, where you don't look at all integer multiples, but only prime multiples. So P runs over primes. So you can ask that question. So here we are not looking at higher degree polynomial, just linear polynomial. So n alpha, and then take integral part, multiply by beta, discrepancy of that. The result is of course worse than what we get there, because it's difficult to handle primes. So I would actually go to a further question, probably a more subtle question. So more subtle question. Oh, that's fine. I probably need 2 minutes. So yeah, so more subtle question. So I'm looking at this real number sitting between 0 and 1. Now what I want to ask, that how their gaps are distributed. Again, in this case, we are again looking at sequences which are already uniformly distributed. So they are already very nice. So now we are going to look at their gaps, and we want to know how the gaps are distributed, how close they are. And that calls for a definition. So this is what is called a pair correlation statistics. There are many pair correlation statistics at many places. This is for this sequence, this particular situation. So let me explain what it is. So I'm looking at pairs xn, xm, and then looking at the difference. But they are numbers between 0 and 1. So the difference might exceed that interval. It might become negative. So we won't do that. So we would look at the nearest integer distance. So if I do that, then I am counting the pairs whose distance is less than or equal to s by n, and then multiplying that number by 1 over n. So that's like a normalization. So that we expect this quantity to go to 2s when n goes to infinity. Yeah. So if that happens, then we say that the sequence has Poissonian pair correlation. It's actually the gaps are distributed as Poissonian. So that's what is playing behind it. So then we, if this happens, then we would say that this has the sequence has Poissonian pair correlation, or PPC to abbreviate it. And all sequences which has PPC are uniformly distributed. It's much finer. And very few examples are known actually, explicit examples are very few. For example, this sequence n alpha, which is uniformly distributed for every irrational alpha, is never PPC for any alpha. That's known. The sequence n square alpha is supposed to have PPC for almost every alpha under very mild conditions on alpha, but even in that case, very small, very few examples have been actually proved. A nice exception is the sequence square root of n. So we are looking at the square root of n, then of course the fractional part. So that has PPC. So PPCs are difficult to prove. So it's interesting to look at what is called metric results. So we are trying to look at from an almost all perspective. So let's just a simple definition. So a sequence of positive integers. Let's look at an increasing sequence of positive integers, an. And we say that sequence has metric Poissonian pair correlation, or MPPC, if An into alpha has PPC for almost all alpha, almost all real alpha. And in a joint work with Tanmay Bera and Mithun Das, so my student and a Mithun was a postdoc in IMSc, so it's an IMSc work as such. So we looked at this question in higher dimension and proved, so this is just a corollary of what we could prove, but it is just easier to state. So let me just explain. So I am looking at two-dimensional sequences. So the first component is fractional part of n alpha, and second component is fractional part of n square beta. Alpha, beta are real numbers. And then we could show that this has Poissonian pair correlation for almost all alpha and beta. So the subtler thing is that when you are in higher dimension, you have various choices of distances. So various choices of norms. So we could prove this in both in 2 norm and infinity norm. Of course, there are infinitely many norms, so and they require a different kind of treatment. And there is another example, it's a little more complicated. The first example is more interesting because the n alpha, the first component sequence, does not have PPC. But when you club it with a sequence which has PPC, it is having PPC. So that's the kind of example we could construct. So I'll stop with that. Thank you for your attention.
So thank you, Anirban, for the nice talk.